Hello, good afternoon, good morning, maybe good evening. Welcome to our seminar today. I'm happy you made it to our seminar on the fundamentals of weathering, part 1, factors of weathering. Um, I'm your presenter today, and you might recognize I am not a native American or not a native English speaker. I'm actually from Germany. My name is Florian Feil. I'm working for Atlas Material Testing Technology as Global Manager for Client Education. I'm also a consultant for weathering technology, and I'm also representing Atlas in mostly the European and some ISO committees together with some of my colleagues. And my background is actually chemistry, so I'm a chemist. I worked, quite a while in material degradation, first with corrosion, later with weathering, but my basic is actually polymer chemistry. And as you might see, my camera is maybe a little bit dark, and it's already getting dark here in Germany. And I work close to our European headquarters in Lindengericht Altenhaslau. And that's who I am and who's your presenter today. And I'm continuing now with a little bit of housekeeping. We have a relatively big audience, and as you might recognize from my greetings in the beginning, relatively some from Europe, but most from the United States and also Southern America, I see. And so, and because we have a relatively big audience, everybody is going to be muted. And however, you have the chance, if you have a question, a comment during the presentation, please take the chance and write down on the question bar on the GoToWebinar control panel. And I will try to have an eye on it during the presentation. I cannot promise, but I will definitely follow up on the questions at the end of the presentation if time allows. And if not, the questions are recorded, and I will follow up on the questions after the seminar in the next days. And and the presentation will also be distributed to everybody who registered with a valid company email address. And after the seminar, there will also be a short survey popping up after the seminar. I think it's only 3 questions, and we would be happy if you can answer to give us some feedback on today's seminar. As mentioned, today we have part 1, factors of weathering. So this is part of a series of different webinars on the topic of weathering, on weathering testing and the principles of weathering. And these webinars, it's more or less standalone webinars, but they fit nicely together in this series. So that's why we present them typically in this series form, but no worries if you miss one. They're going to be repeated at some point. And currently we are starting with a new series, and I think we try to cover different time zones, but there will be other series of these seminars coming up in the next weeks and months. So if you miss something, it's not a big thing. You can watch them later or look at our recorded seminar as well. Who are we? Who is Atlas Material Testing Technology? Atlas Material Testing Technology is a manufacturer of weathering and corrosion test instruments. So we have a broad range of instruments, of different instruments. You might know our big instruments, the weatherometers. We have medium-sized Xenotest equipment, SunTest equipment as well. So that's our main focus as manufacturer, but we also have test services. We have big laboratories, weathering test laboratories in the United States, and our headquarters in Mount Prospect, close to Chicago. But also here in Lindengericht Altenhaslau, we have a big test laboratory to cover the European market. We have Atlas Custom Systems. Atlas Custom System designs and build custom solar simulation lighting system solar simulation solutions, I must say, for larger scale testing, solar load testing, or for the illumination of wind tunnels, for example, or bigger climatic chambers also. And yeah, lastly, we provide technical weathering support, we provide consulting, we provide client education, and we are active in standardization. And that's, yeah, mostly part of my work I'm doing. So this was the commercial part. Now we go into the topics of weathering. Today we will go into the factors of weathering mostly. And yeah, we will not go so much into weathering testing. This will be covered in the upcoming seminars. Today is to understand the effects of weather on materials. Yeah, polymers and other materials degrade by the effect of weather, by the effect of the environment, by the effect of solar radiation, but also of other environmental factors. And very, very obvious, very often is a visual change. Very often is color fading is a primary result of weathering degradation, weathering effects on materials you see in the field. And I think everybody of you knows a traffic sign nearby which is faded, or a car which is faded. So that's a typical appearance change by the effects of wearing. But other effects can happen as well to materials, bulk materials like chalking, when the surface gets a little bit powdery. That's very often appearing. Yellowing is a typical appearance change, or gloss loss as well. However, there are other appearance changes, not necessarily visual appearance changes, but there are other changes possible, because weathering or light degradation affects not only bulk materials, it affects every type of organic materials, and this includes also food and beverages, for example, or cosmetics. And these products, they might not change visually, but they might change their taste or their odor. And that's also an appearance change which can happen. And that's typically only what we see, but there can happen also a lot of other things to the materials by the effects of weather. Very often, it's not only that the dye stuff is degrading. Very often for polymers or for coatings, also the matrix is degrading. So the polymer, the coating becomes mechanically weaker. So very often you observe that materials get brittle, surfaces crack, or you see delamination, in general a loss of strength of those materials. And there are a lot of other effects related to weathering degradation. The active ingredients can get degraded. And that can be an issue, for example, for pharmaceutical products. When the active pharmaceutical component is degrading by the effect of weather, the pharmaceutical product loses its purpose, so its function. And that's a really severe effect of degradation. But also polymers consist of many additives, flame retardants, herbicides, fungicides are added to a polymer to provide protection for the polymer. And those additives actually can degrade. You don't see it. Maybe the mechanical properties do not change, but the properties in general of the polymers, of the coating, can change. And if you look for those properties for your product, and you test your product for weathering stability, and these are the relevant properties of your product, you have to check those relevant properties after the exposure, after weathering, to see if the product is still good enough for its purpose. Yeah, the primary weathering factors causing degradation in the environment in the relation to weather, we consider solar radiation, temperature, and humidity, water in its different phases, which can cause degradation. And it's not only about the quantity of those factors, it's also about the quality, the spectral irradiance distribution, the temperature. Is there a maximum temperature, minimum temperature? Are there specific times at a specific temperature? Are there temperature cycles? And similar for moisture. Moisture is typically not a continuous factor. It's typically a cyclic factor. You have wet phases, dry phases. So you have also typically a cyclic stress. And all of those primary varying factors, and most often together with oxygen, which is always present. So we don't necessarily consider oxygen as a primary varying factor. They cause a chemical stress to an organic material, to a polymer, and they cause chemical degradation. And first, you get some microscopic chemical damage. You might not see it. You might not have a severe influence on the tensile strength, for example. However, at some point, this damage is accumulating, it becomes more obvious, it becomes more visible, and then you get macroscopic damage, very often physical damage, cracking at a secondary, I would say, effect of weathering. And secondary varying factors are also present in the environment. Secondary varying factors we could typically consider pollutants, biological factors, acid rain, and or sea salt, for example, can be considered as a secondary varying factor. They are typically also present. They also contribute to the degradation on materials, but in artificial weathering, we typically need to reduce the stress factors to the primary weathering factors to some reason, because it can, on the one side becomes too complicated, and those secondary weathering factors are sometimes hard to simulate. To be realistic, they should be included, but again, it becomes a little bit complicated. However, in reality and in weathering testing, it's important that in nature, those varying factors, they act together, they act synergistically, and to get realistic test results, if you try to simulate those effects, you have also simulate those effects simultaneously to get the same synergistic effects as in nature. When we talk about weathering, we talk about typically material degradation in an outdoor environment. And outdoor means we have solar radiation, we have heat effects by the sun, by the environment. But typically what we have in an outdoor environment is also water in the form of rain, in the form of dew. So weathering typically includes liquid water. When we talk about light fastness, photostability testing, sometimes just called irradiation testing, then we typically focus on mostly the light, but generally we have relative humidity present, we have temperature effects, but no liquid water. And that testing is typically done for interior materials where we don't have liquid water, we don't have rain. So typically textiles, interior furniture, wallpapers, food and beverages, pharmaceuticals are typically tested for an interior climate. So typically photostability or light fastness testing, no liquid water. Let's go through the different varying factors, starting with radiation. We will look at radiometric quantities. We will look at how solar radiation actually looks like, how it's measured, and how, very briefly, how it affects materials. So solar radiation, it's actually a part of the electromagnetic spectrum. And solar radiation actually ranges from the UV range to the infrared range, and the visible range is in the middle. And so the sun is emitting UVC, UVB, UVA radiation. So UVC from about 100 to 280 nanometers, 280 to 315 nanometers is UVB radiation. UVA, it's 315 to 400 nanometers. Visible radiation, that's what actually the human eye can see. It's typically considered to be the range from 400 to 800 nanometers, but these are not necessarily exact numbers. Everybody has a little different side. There are a little bit different definitions, but for us, we like it simple, 400 to 800, it's visible part. And everything above 800 nanometers is infrared radiation. And the critical thing about this irradiation is the shorter the wavelength, the higher the photon energy. So the UV photons actually have the highest energy, and that's why, it's not a mystery that UV can cause material damage, and it can be critical to material degradation. The sun is emitting all types of irradiation, not with the same intensity, not with the same irradiance. That's what we call it in weathering. The solar spectrum is actually starting from the UV range, ranging over the visible range into the infrared range. So sun is emitting radiation maybe up to 4,000 nanometers, but the intensity at higher wavelengths becomes relatively low. And the sun is almost behaving like a black body emitter. That's a body which is emitting irradiance independence from its temperature. And the sun is behaving almost like a black body emitter of 5,250 degrees Celsius surface temperature. However, that's what the sun is emitting, but in between the sun and our position on the Earth, we have the atmosphere. And the atmosphere is acting like a filter to solar radiation. So especially the outer ozone layer is cutting off actually most of the UVC radiation. And that's a good thing because UVC, low wavelengths, high energy, has a lot of energy. Photons are very critical, can destroy organic materials. Should be avoided to be exposed to UVC, and the atmosphere is protecting us from the UVC radiation, and it's filtering out many other parts of the emitted spectrum. And what we in principle get when the sun is filtered by exactly one atmosphere is what we should see in red here, and that's the so-called air mass 1 sun, when the sun is filtered by one atmosphere. And that's the case at sea level when the sun is perpendicular, so at the equator at the 21st of March, and on a clear sky at noon. Then the sun is perpendicular, and then we have about this spectral irradiance distribution shown here in red with the specific absorption bands of specific components of the atmosphere. Don't want to go too much into detail here. However, that's just the spectral irradiance distribution at noon. However, the sun is only shortly at noon and only at the equator or at the, between the tropics. In Germany, the sun is never perpendicular, so we'll never see the air mass 1 sun. Actually, here air mass 1.5 sun is much more realistic. However, I just did here a rough calculation how the actual spectral irradiance distribution would look like at different times of the day. And as you see in red, that would be the mass 1 sun we saw on the other picture. And the most time of the day, the irradiance is actually much lower. Yeah, coming back to this reference air mass 1 sun, and like many things, everything is standardized, everything needs a standard to be referenced. And especially if it comes to material development, material testing, I just get the message that there is no audio. It looks like I have audio. From my side, it's working. So maybe it's only a single message I got. Maybe it's your computer. Maybe you have to reboot it. Sorry for that. There's a reference done, and this defined by the International Commission of Light. And they actually some years ago did a very extended calculation to calculate the reference sun, and this was published actually in the publication number 85, table 4. It's the reference sun when the sun is exactly filtered by 1 atmosphere. And that was for many years the reference sun we have been using in weathering. However, this was recalculated and recently republished as CIE 241. And here it's not table 4 anymore, it's CIE H1 is a reference sun, which is more or less the same sun as the old reference sun, but the resolution is better, it's better calculated, a better model. It's relatively similar, it's not identical. And in the near future, our weathering standards will change from referencing CIE number 85 to reference CIE 241, but that's unnecessary background information now at this point, I would say. What's more important is at the reference sun has about 7% UV, so a relatively small portion, about 55% visible radiation and about 38% infrared radiation. And again, the higher the photon energy, the higher the shorter the wavelength, the higher the photon energy, the other way around. And the more critical actually the photons are. And that's the reason why UV photons are the most critical, even if it's only 7%. Here we typically observe the most damage. However, the lower parts, the blue light, the purple light, the high energy visible radiation can also cause direct photochemical damage. However, the longer wavelength visible radiation and the infrared radiation typically does not cause direct photochemical damage, however, can heat up materials. To quantify solar radiation, we are not so much interested in the output of the light source. We are interested in what's received on a surface. And the irradiant power on a surface is what we call irradiance. And the unit here is watts per square meter. And the symbol for irradiance we typically use in E. So energy flux on a surface, intensity on a surface, that's the irradiance. And we can look either at the full irradiance or we can look at a specific wavelength, at a specific, 340 nanometers, 420 nanometers as the spectral irradiance, the irradiance, the intensity on a surface at a specific wavelength. That's the spectral irradiance. If we want to know the full amount of energy in a specific time frame, which is delivered on a surface, we look at the radiant exposure. And that's the time integrated irradiance, so energy per surface. And here the symbol is typically an H. So we have an annual radiant exposure, the full amount of solar energy on a specific surface in a specific area. That would be radiant exposure. And also here we can look at the full radiant exposure or the spectral radiant exposure. To measure solar radiation, we typically use so-called radiometers, so a device which is designed to measure solar radiation. And there are different types. There are so-called pyranometers. They measure, typically the global radiation, the full amount of radiation, all wavelengths and all directions. And a pyranometer can be relatively similar. It can be just a painted pieces of metal, black and white. And by the temperature difference between the black and the white area, this simple pyranometer can be calibrated to measure the global radiation. However, today very often photodiodes are used or other photosensitive elements are used as pyrometers. Pyranometers are relatively similar, but they measure only the direct solar radiation, so no diffuse solar radiation. So typically a pyranometer is a also a similar sensor, but it's on the bottom of a tube so that only the direct solar radiation can hit the sensor. Then we have the high-end instruments, the spectroradiometers. They can actually measure the solar radiation wavelength by wavelength. So that gives you this full amount of the spectral irradiance distribution. Very good to have, but very complicated to monitor continuously a light source with a spectroradiometer. So typically not done to monitor long-term exposures, for example. Filter radiometers are relatively similar to pyranometers. So you have a photosensitive element, but covered with a bandpass filter, which is only transparent within a specific bandpass of the wavelength, so between a specific wavelengths. And that's what we commonly use in weathering, outdoor weathering, artificial weathering, because these are relatively simple instruments, but you can relatively controlled look at a specific wavelength range. So, and there are narrowband filter radiometers, typically wavelengths half-wave wavelength ranges between of less than 20 nanometers. There are broadband, so in a medium wavelength half-wave range, and wideband filter radiometers available. We will see examples of these measurements ranges on the next slide. So typically, when we look at the spectral irradiance distribution, we are interested in the intensity, so the irradiance and the full amount of energy in a specific time frame. And so give you some somehow typical numbers. These are not maximum numbers, these are not specific numbers, but a typical irradiance value, if you look at the total irradiance from all wavelength ranges, is about 1000 watts per square meter. If you look at the reference sun is a little bit higher, but it's a typical maximum value we consider as one sun level. And for example, the annual radiant exposure in Miami, so the full amount of radiant solar energy delivered on a surface in Miami is about 6.7 gigajoules per square meter, if you look at the full range. However, you can just look at the UV and the visible range, and that would be a typical wideband radiometer range. So there are wideband radiometers available which just look at the wavelength range from 300 to 800 nanometer. And here the equivalent value actually would be 550 watts per square meter as irradiance and about 3.6 gigajoules per square meter radiant exposure. And you can look at the total spectrum, just look at the UV range. If you use a broadband radiometer, and here typical range is from 300 to 400 or 295 to 400 nanometers. And here the equivalent value would be about 60 watts per square meter from the irradiance and about 400 megajoules per square meter annual UV radiant exposure from 300 to 400 nanometer. Or you look just at one wavelength with a narrowband radiometer, and here the spectral irradiance in the almost middle of the UV at 340 nanometers would be 0.51 watts per square meter and nanometer as spectral irradiance at 340 nanometers. And the annual radiant exposure, the annual spectral irradiant exposure at 340 nanometers would be about 3.3 megajoules per year. So in principle, if you would look at the sun with these different types of radiometers, these would be the values you measure as irradiant and as the irradiant exposure. I mentioned it briefly. I typically talk about total solar radiation when it's about all wavelength ranges. However, sometimes you hear the term global radiation, and global radiation means solar radiation from all directions. And that all radiation is hitting a surface directly from the sun, or is reaching a surface directly from the sun. Because, as mentioned, we have the atmosphere in between the sun and the surface, and the sun is acting like a filter, so some parts are filtered out, some parts are reflected, but also some parts of the light are scattered. And there are different types of scattering. There are particle scattering with Wolken, which is the German word for clouds. I have to correct this in the slides. And particle scatter solar radiation independent of the wavelength. So no matter which wavelength, it's scattered into all directions almost similarly. So clouds or particle scattering does not change the spectral irradiance distribution. And the human eye is actually trained to observe the global solar radiation, the light of the global solar radiation, the visible part, as white light. And that's why clouds appear to be white, because there's no shift in the spectral irradiance distribution. However, there is also molecular scattering, also called Rayleigh scattering, and that's wavelength dependent. The higher the photon energy, the higher the interaction between the molecule and the photons. And that's why short wavelength photons are scattered more compared to longer wavelengths. And short wavelengths means for the visible part, the blue part is scattered more compared to the red part. So a solar beam which is not directed into my direction, I typically would not see if there would be no atmosphere, but the atmosphere is actually scattering this solar beam, and it's scattering the blue part more compared to the red part. That's why the light I see coming from the atmosphere, from the sky, appears to be blue, because of Rayleigh scattering. Same reason, especially in the evening when I look directly in the sun, which is never a good idea. But anyway, the reason the sun looks yellow and maybe reddish in the evening is there's a deficiency of the blue light due to Rayleigh scattering. That's why we get the shift into the other direction. Less blue radiation makes the light appear to be yellowish, reddish. So that's Rayleigh scattering. And why I'm telling you this, we have a lot of diffuse radiation, especially in moist atmospheres like Florida, but also Europe, Northern America, and moist environment. When you have clear sky but a lot of moisture in the air, and water has a big effect on Rayleigh scattering. And with this Rayleigh scattering, you get a lot of diffuse light, and okay, there's no direct light, but the diffuse light can be rich in UV. And that's the reason why you can even get sunburn in the shadow, because of Rayleigh scattering. And here just two other calculated examples to show you the effect of Rayleigh scattering. In green, we have the global solar radiation, and global radiation is the sum of direct and diffuse radiation. And in purple, we have the diffuse radiation, and red, the direct part. And if you have a moist atmosphere, here 80% relative humidity, but still clear conditions, you get a lot of Rayleigh scattering. And actually in the lower wavelength part of UV, you have even more UV in the diffuse radiation with this calculation, with this model, compared to the direct part. In a dry area like Phoenix, for example, not much humidity in the air, so not much or less Rayleigh scattering. There's some Rayleigh scattering going on here, but not such a big effect like for Miami, for moist atmosphere. So another effect on the spectral irradiance distribution on a surface is the so-called albedo reflection. This is relevant for inclined surfaces because you have an additional factor, reflected solar radiation from the environment. Can be a factor in urban environments where you have a lot of glass facades, typically mostly reflecting in the visible range, but there are ground covers which reflect some UV also, and this radiation contributes also to the radiation received on a specific surface. And so you have to know the ground cover where your specimen, where your samples, where your surfaces are, to understand all of this. And just to give you some numbers. And again, the reflectance, it's also a spectral value. So the spectral reflectance depend on the ground cover, and different regions of the spectrum are reflected differently dependent on the ground cover. Yeah, it's more complicated than just sunlight. And it even becomes more complicated. The amount of solar radiation received on a surface depends on the exposure angle. When the sun is perpendicular, and that's what we call direct normal incidence, we have the highest intensity, the highest irradiance. And the irradiance actually decreasing with the cosine of the angle. The sun is hitting the surface. So you get the highest amount of solar radiation when the sun is perpendicular, nothing new. In Northern Europe, in Germany, our vineyards are typically on south-facing hills, very steep, to catch as much sun, especially in summertime, as possible, to optimize the exposure of the grapes. And same is typically also relevant for materials, for products exposed to environment. So in the northern atmosphere, on the 21st of March, for example, when the sun is perpendicular actually at the equator, a horizontal surface is not at DNI at this time of the year. However, what you can do, you can incline your exposure surface towards the sun. And if you do this at the latitude angle you're at, you can actually mimic a perpendicular exposure with your test specimen, even on the northern atmosphere or in the southern atmosphere far away from the equator. You still have the longer wavelength, the path length through the atmosphere with the light, but you at least can optimize the exposure angle to catch as much solar radiation on the surface as possible. And so the amount of solar radiation depends on the exposure angle. And each time of the year at noon, the sun is at a different position. So our horizontal surface might be better in summertime in the northern atmosphere compared to an at latitude exposure. So it depends on the time of the year which angle actually would be the best angle for the exposure. So, and this definitely also influences the pattern throughout the year. So it's important to know the surface orientation your product will see or the data you receive are from. That's very important to consider. And just to give you also some examples here, how it can look like. Here we have the exposure angles of 5 degrees, which is almost horizontal. We have 34 degrees at the latitude angle of Phoenix, Arizona, and 45 degrees, which is a commonly exposure angle used in weathering for historic regions. And compared those, on the one side, the total solar radiation, which is relatively evenly distributed in these inclined exposures. So we mimic a tropical exposure, a horizontal, not horizontal, a tropical, an equator exposure in principle with the inclined surfaces, so it's more evenly distributed throughout the year. In summertime, it's not the optimum angle, so the horizontal surface receives actually more solar radiation, and in wintertime, it receives less solar radiation, so it's more evenly distributed throughout the year. And if we look at the radiant exposure throughout the year, it's actually also the maximum radiant exposure for the latitude angle inclined towards the sun. In the UV, the effect is not as big. Why? because we can only influence the direct share of solar radiation with the exposure angle. The diffuse solar radiation acts more or less the same on each surface, and there's a lot of UV radiation in the diffuse part, even in Phoenix. So the effect on the UV is not as strict as for the total solar radiation. So that's also something which has to be considered. Briefly, to look at the maximum natural irradiance we see typically in the field, in the outdoors. And I mentioned it briefly earlier, it's about 1,000 watts per square meter. And typically what we consider maximum irradiance in the UV, it's about 60 watts per square meter. So a typical, not worst case, but a typical maximum value which happens in nature. And here, just for your reference, to give you an overview about typical annual radiant exposures from our exposure sites throughout the world. We have exposure sites in Miami, in Phoenix, but also one in Europe, in Sanary-sur-Mer, in Hoek from Holland, in the Netherlands. And yeah, just for your reference, you can look at those numbers. And one thing I just briefly want to point out, for historic reasons, in outdoor weathering, we typically use filter radiometers from 295 to 385 nanometers. In artificial weathering, for historic reasons, we typically use UV filter radiometers from 300 to 400 nanometers. So be careful if you hear about UV data from outdoor exposures when you convert those for artificial exposures, because the range can be different. But you can roughly transfer it with a conversion factor from one to each other, typically for natural solar radiation at least. Yeah, here's just for your reference also a world radiation map to give you some idea which areas in the world receive a lot of solar radiation. So typically that's not the tropics where the solar angle actually would be the best, but the tropics are very often cloud covered where I have a lot of rain. So, and that's again filtering out a lot of solar radiation. So actually, the highest amount of solar radiation is observed at the tropics, in the northern atmosphere and in the southern atmosphere, and in high altitude areas. Yeah, the effect of solar radiation on organic components. First, solar radiation has to be absorbed to cause an effect. This effect can be, if solar radiation absorbed, that the molecule is transformed from its electronic ground state into an excited state. So you have an excited molecule, which has a lot of energy. And typically an excited molecule wants to get rid of this energy. And mostly this energy is emitted in the form of heat or in the form of light, fluorescence, phosphorescence. However, sometimes, and that's relatively seldom, but sometimes it can happen, this energy is causing a reaction, for example, with oxygen or other components, and then the photodegradation is starting. Photodegradation processes can be photooxidation, other processes typically involved with radical reactions. And radical reactions are typically chain reactions. So typically one photon causing the resulting in in a radical can cause multiple damages in a polymer. So, but we have other seminars just focusing on photodegradation, so I don't want to go into detail on that here at this point. The spectral sensitivity of a material describes the wavelength range where the material is sensitive to photons. So, and typically the material has some spectral sensitivity in the UV. It does not necessarily be only in the UV, it can also be in the visible range, especially dyestuffs very often have specific spectral sensitivity in the visible range. And on the other side, you have the light source, the radiation source. And in the areas where you have photons present and you have a spectral sensitivity, so when the two curves overlap, that's the area where you can actually observe degradation. And the higher the photon energy, the more severe the degradation. And the overlapping area can also be calculated, and that's the so-called activation spectrum. And that's a very material specific properties. So, and if you shift the light source to an unrealistic UV cut-on, you get a different overlap. You might get an overlap with other spectral sensitivities. So typically one material does not have a single spectral sensitivity, can have different spectral sensitivities resulting in different reactions. So if you have an unrealistic UV cut-on, you typically get unrealistic degradation. Yeah, to summarize on solar radiation is influenced by the atmospheric conditions, by the pathway through the atmosphere. So it depends on the area you are, the season, the daytime, the weather conditions, and how the surface is oriented. And solar radiation is actually initiating photochemical degradation, which leads us to the second factor of weathering, and it's a little bit shorter than the other one. I might not be completely finished in 15 minutes, but I try to be on time as possible, so maybe 10 past the hour I should be at the end. Temperature of irradiated surfaces are described, how they are measured, and what effects we are going to have. And it's actually not a big surprise. Everybody knows this. The darker a surface exposed to solar radiation, the higher the surface temperatures, typically. So, and here we just exposed PVC-coated aluminum plates in Phoenix, Arizona, again, throughout several days, and we measured the surface temperatures, and we see, yeah, no big surprise. All surfaces, even the white one, gets hotter compared to the ambient temperature. And the higher the irradiance during the day, the higher the temperatures. And we see this temperature splitting between the different colors. So no big surprise. And actually, let me go to this slide first. So we have the solar radiation coming in on the surfaces. However, there's also thermal radiation. And each body in a field in the environment is emitting heat energy at a much longer wavelength range compared to solar radiation. And in an outdoor environment, we have a lot of incoming energy from the global radiation, depending on the absorption, on the reflectance, so on the color of the surfaces. And on the other side, we also have incoming thermal radiation from the environment, and we have thermal emission from the surface we are looking at. And during daytime, we have a specific balance, which is on the positive side. So we have more incoming energy compared to the energy loss. So we have a heating up of the surface during the daytime. However, at nighttime, when there's a clear sky, the sky has relatively low thermal emission, but the surface is still losing thermal energy. So it's losing actually at nighttime more energy than it's receiving. That's why at nighttime, surfaces gets cooler compared to the ambient temperature, to this thermal emission effect, to the radiation heat balance. Yeah, that's actually the same described here. In daytime, you have the solar heat coming in, but you also have thermal emission from the surface. You have the incoming solar radiation from the environment as well. So you have the thermal heat balance. In nighttime, you don't have the incoming solar radiation, but you still have the balance between the environment and your surface, but that balance is on the negative side, so you lose more energy, so the surface gets cooler. There's a specific case when you have a separate area. That's a typical greenhouse effect when you have a surface in an enclosed cabin. And an automotive cabin typically has windows, and through the windows, solar radiation can pass through. Mostly the UV part is filtered out, but the visible part can pass, maybe some infrared part can pass, and heating up the surface inside the cabin. And the surface in the cabin, the seat, the windshield, or the armature shield here, and the other parts inside the car are heated up and emitting energy. However, now you have an enclosed cabin and you have the glass between the environment and the and your surface. So this exchange with the environment is actually prohibited, and you have the glass, which is also a thermal emitter acting into both directions. So you get a greenhouse effect. You get this extreme heating on those surfaces in the interior of a car, and that's the greenhouse effect in the interior of a car. So just to give you some numbers on typical maximum daily ambient temperatures we observe in our outdoor fields, we have here data from Chennai in India, Miami and in Florida, Phoenix, Arizona, Hoek van Holland in the Netherlands, and Zonnarue-sur-Mer in southern France. And what we see here is the frequency of occurrence in a 6-year frame, how often specific daily maximum ambient temperatures occurred. So and we especially in Chennai and Phoenix, we frequently see temperatures above 40 degrees Celsius, air temperatures, not so often in Miami and in the European countries, not so often. So 40 degrees Celsius, I would say it's a relatively realistic maximum temperature in an outdoor environment, and many weathering standards have maximum temperatures or chamber temperatures, air temperatures in the range of 40 degrees Celsius, so relatively realistic. However, in weathering, we are much more interested in the surface temperature of our test specimen. And in general, it's relatively complicated to measure the surface temperatures of individual exposed samples. And that's why in weathering, we use reference temperatures. And of course, we want to have somehow the worst case reference temperatures. And that's why we use black painted metal sheets, black painted metal panels as reference temperatures. Unfortunately, there are two different types of black standard sensors defined. The so-called black panel sensor is a black painted metal sheet without insulation on the backside. And the black standard sensor is very similar, but it has a polymer insulation on the backside. So it shows a little bit higher temperatures compared to the black panel. The problem is the surface temperatures also depends on the airflow, the wind speed, and the environmental conditions, not only on the irradiance and the surrounding air temperature. So there's unfortunately not a fixed difference between the black panel and the black standard temperature. Typically, under irradiation, black standard has a higher temperature. However, the difference can be 2 degrees, it can be 10 degrees, depends on the whole setup of the system. And that's a little bit unfortunate. So the reason why we have two different types of sensors, it's a little bit historic. American standardization for many years preferred and used the black panel sensor, which is shown here on the right. ISO standards prefer historically the black standard sensor. Most standards today allow both options, but the results may be different because of the unknown temperature difference. So be very careful when you test according to a standard in selecting the right sensor type. That's very critical on the degradation. And there are similar sensors to represent the lower limits of opaque surface exposed to the environment, and it's the white panel or the white standard sensors, relatively the same. And also here to give you some numbers, the frequency of occurrence of specific black panel or black standard temperatures at the same sites in India and the US and in Europe. And again, Chennai, Miami, Phoenix, sometimes we observe surface temperatures above 70 degrees Celsius, very seldomly above 80 degrees Celsius with these sensors. And coming back to standardization, standards very often use black panel or black standard set points in the range of 65, 63 degrees, depends on the sensor type you're using, which appears to be relatively high. But you are not at the worst case conditions. You are at relatively normal maximum conditions, I would say, with these temperatures. So again, standards here for weathering relatively realistic to give you some numbers. Why are temperatures so important? Very briefly, temperatures influence the reaction speed. And this also applies for degradation reactions, photochemical degradation processes. The higher the temperatures, the faster the degradation. There is a very rough rule of thumb, and I hear some of my colleagues from standardization already yelping right now because this rule of thumb is really very rough. It most often does not apply. It's most often disobeyed. But to give you some idea of effect of temperature, a temperature decrease of 10 Kelvin doubles the degradation rate. That's can be the magnitude of effects of temperature, but the exact influence of temperature actually has to be calculated, and there's the so-called Arrhenius equation where you have to consider other factors like activation barrier and so on to really calculate the effect of temperature increase on material degradation. And this real effect, this real acceleration rate by temperature is very specific to the polymer, to the material, and also the property you're looking at. It can be much less than the 10, than doubling the reaction rate. It can be much more than doubling the reaction rate. So just to point this out. Another effect of temperatures on materials is the material phase. Temperature increases can cause phase transitions, melting, but also almost noticeable phase transitions like the glass transitions. A polymeric material typically has a glass transition temperature. Below the glass transition temperature, it's more, harder, it's more vitreous, glass-like. Above the glass transition temperature is more rubbery, more elastic. And of course, reaction rates, diffusion rates are different below the glass transition temperature and above the glass transition temperature. So the influence of weathering effects will be different. And in reality, you test your material as close to the real conditions as possible. And if it's only maybe above the glass transition temperature throughout maybe through minutes of the day, or maybe only once a year or twice a year, and you test continuously above the glass transition temperature, you test in principle the wrong material. So you have to be very careful with the test parameters in artificial testing to consider an appropriate temperature for the glass transition temperature. That's very critical. And most often, one of the most reasons I don't see good weathering results, or very often, is that the glass transition temperature is not considered. That's very critical. And just to give you some examples of typical glass transition temperatures, glass transition temperature depends always on the formulation of the polymer. So these are not exact numbers. So elevated sample temperatures cause higher diffusion rates, higher reaction rates, phase transitions. Effects of heat can be expansion, contraction, so a mechanical effect. Evaporation, condensation can happen. So evaporation of additives, but also of water, condensation of water at lower temperatures. And there can be also thermal aging. This brings me to the last and the shortest weathering factors, factor moisture. We will briefly look at quantified typo here and effects of moisture on materials. So typically to quantify moisture, to give you some value, some expressions here, some terms here is the absolute humidity. It's not so commonly used. That's the density of water vapor, the density of air, so in grams per square meter. What you more commonly see is the relative humidity, the amount of water in the air. But this factor is actually the relative factor, because this amount of water vapor is compared to the amount of water vapor the air can hold when it's saturated. So the percentage of saturation. And the hotter the air, the more water it needs to get saturated. Sometimes we see the dew point as a quantification of air moisture, and the dew point is actually a temperature. It's the temperature at which the air starts to condense when you cool it down at a specific relative humidity, for example, a specific absolute humidity. So that's the point when the relative humidity actually reaches 100% when you cool down the air. Then a very important factor is the time of wetness. That's just the time a surface is wet in the environment. So a wet can mean by rain. And here we have the average monthly rain from our outdoor sites, average over several years at the different sites. And obviously, Miami, Chennai, subtropical, tropical climates, very high amount of rain, so a lot of moisture. There are some seasonal variations, but general, each month, very wet. Then we have Sanary, Sumer, a lot of rain in wintertime, not so much in summertime, and Hoek van Holland in the Netherlands, a lot of rain throughout the year, I would say. And it's Hoek van Holland, it's Northern Europe, middle Northern Europe, I would say. It's cold rain, not a pleasant weather. However, Phoenix, also some rain in wintertime, but almost no rain in summertime. So overall, the lowest amount of rain. Then we have the relative humidity at these locations, and actually showing here in the bigger bars here, the average relative humidities at those sites, and we see a similar order like on the with the rain. And Phoenix also is the lowest amount of relative humidity. But what you actually have to look at, and you might see it on the screen slightly, it's the upper and the lower limits here for each location. That's the range of the relative humidity, and typically, again, average value shown here. But relative humidity is typically very high at nighttime because the temperatures are low, and the relative humidity is typically low at daytime because the temperatures are high. So that's typically the upper and the lower limit, which shows up here, is actually the average daily cycle of relative humidity you experience in the different locations. And if you look at Miami, Phoenix, but also, Hoek van Holland, the Netherlands, you're almost at nighttime close to saturation. So it's close to dew formation, actually. That's the next slide. Typically, throughout the day, you have the maximum temperatures, somehow in afternoon, after late mid-afternoon, maybe you have maximum air temperatures. And as mentioned, the relative humidity percentage of saturation, hot air can pick up more moisture. So typically at daytime, the relative humidity is low because the air is warm. At nighttime, the relative humidity is high because the air is cool. However, if you look now at surface temperatures, and they heat up mostly during daytime, but they cool down, and they cool down below the air temperature at nighttime. And at the boundary climate between the air and the surface temperatures, you get into actually oversaturation much easier. And that's the time of the day you get dew formation. So time of wetness on the one side by rain, but even more critical is the time of wetness by dew. And that's the case in tropical, subtropical environments, Florida, Chennai, but also Europe, Northern America. Many areas have dew formation almost every day. So a critical factor of weathering is done by dew. And that's, very important. And in reality, we can measure the time of wetness, which is a little bit complicated. So we measure it continuously, but the data, that's another story. But here we have some data at different angles on on time of wetness, actually measurements in Florida. And we see we have some dependence on the exposure angle because of the amount of rain which is received on the surface, but also on the fastness of drying when the sun is shining, and also how fast the water is pouring off does all influence the time of wetness. But overall, it's about 50% of the time a surface is exposed in Miami, the surface is wet. And it's a really critical factor. And Phoenix, on the other side, much lower time of wetness. Yeah, here just briefly, how do the different weather factors actually interact with each other? So we have actually, let's start with the solar radiation here on a clear sky day in Miami, which is relatively seldom, where you have no clouds at all, and you see the UV irradiance rising during the day, reaching a noon maximum at noon. Following that is the air temperature shown in red here, and the black panel temperature shown here in black. And yeah, a relatively warm day, 50 degrees black panel, 30 degrees air temperature. If you look at the relative humidity, it's close to saturation at nighttime, getting to 50% during daytime, and then back to close to saturation at nighttime. From that, you can actually calculate the absolute humidity and the dew point. And this is actually relatively interesting that the absolute humidity throughout the day is actually in the air, it's relatively constant. You have a slight increase in the morning through the drying of dew, but it's not changing very much. So the total amount of moisture, the absolute amount of moisture in the air is a relatively constant factor. It's more seasonal varying in Miami. So the different factors influence each other. And the critical part about moisture is very often the moisture cycles. And very often these moisture cycles are relevant for polymer or coating degradation. And here we have an example where a coating was exposed to spectral irradiation, and there was actually only yellowing with just irradiation. But if moisture cycles have been applied, then cracks occurred. So crack formation, surface cracking is very often a combination of aging by photochemical aging and cyclic stresses by moisture cycles. So for realistic simulation, moisture is very critical. And there are other effects of moisture like thermal shock, which is relevant. There's erosion effects, impact effects, and there are also degradation reactions, especially for hydrophilic polymers, which can be only caused by water, by humidity, hydrolysis effects, and so on. There are a lot of secondary weather factors. I briefly mentioned them in the beginning. It's hard to simulate them. You can simulate them, somehow in the field sometimes, acid rain, microorganisms, and others. I will not go into details here, but you have to consider them if you transfer your test results to reality. Yeah, to understand the effects of the environment on your material, you have to understand the environment, you have to understand climate. Climate is what we expect, weather is what we get, Mark Twain said. And there's a difference between weather and climate. Weather is the status of the atmosphere at a specific point of time, and climate typically describes the long-term pattern. So if you produce or develop a product for a specific market, you have to understand the climate in this market. And there is some guidance given by the so-called Köppen-Geiger classification, which is somehow simplifying different climate types into a 2 or 3 letter code describing the climate. So arid, Mediterranean, and moist, or moderate with wet summers. So it's relatively good described, and it's actually freely available. But I think it's written here somewhere, the web page, or if you Google Köppen-Geiger, you get the whole classification for free for download from some sources. So it's not complicated to get that information. It gives you some ideas on a climate for a specific region, if you develop a product for a specific region. And that's what we typically do. I mentioned I work in consulting, and we develop test programs for many products in the history. And what we typically first do is to start with a climate analysis. And if the product goes into different areas, and here's in the product which was used for transportation, for aircrafts and for ships. And we first start with a climate analysis of all the regions the product will see. And we do some assignments according to Köppen-Geiger, compare the environmental parameters, and we see the different areas group up. So you get some idea of those behavior of the stress effects in those different climate areas the product will actually end up. It's probably not as complex for many products as here, but that's how to start with, to understand the weather factors. And if you understand the weather factors, you can understand how your product will actually react to the weather factors. And that's it for today. Actually, next week we will go into outdoor weathering. Actually, don't know if I'm going to present or if one of my colleagues is going to present. I think it's one of my probably native speaking colleagues who is going to present next week on outdoor weathering, on the test site, on the outdoor weathering technology. Yeah, please use our knowledge resources. You find them on the web, and when you get the presentation, you get all these links you can directly click on to find our knowledge resources. We have a relatively new weathering blog, which is currently populated. I think I already posted one post, and yeah, please follow us on LinkedIn, and for future seminars, and you found this seminar today, please visit our client education calendar. I already talked a little bit too long, and I don't see any incoming questions. If I don't see any incoming questions, you have our contact details. Please, you can write us your questions anytime afterwards. The presentation again will be distributed, and please take your time to fill in the short survey after the seminar. That's it from my side. Yeah, you're welcome. And I hope we meet each other as another seminar. Have a great day or a great evening, and goodbye. Thank you.